Today we're going to learn the topic cross-validation and hyperparameter tuning. So what is cross-validation? To start with, this is a fantastic topic. So okay, what is the core problem and why do we need cross-validation or validation? Okay, we need to understand that. So before introducing the complex techniques, it helps to ground what topics and why we need them, okay, to understand the ultimate goal, underfitting and overfitting. So ultimate goal, we want a machine learning model that generalizes well to new unseen data rather than just memorizing the answers. So we know two terms before, right? One is underfitting and one is overfitting. So what is underfitting? Underfitting is high bias, means this occurs when the model doesn't train well on training set and a result performs poorly on the test set. That means whatever it learned, it will give high biasness. Okay. And overfitting means when you're giving too much data, that is high variance. This is when the model learns the training data too well, failing to generalize to new data. Okay. That is high variance. The basic approach is the So if you see here, why do we need cross validation? We have seen here overfitting. The model doesn't train well on training data set, as I have said. So this is overfitting, high variance, underfitting, high biasness. That means it will go in one style because it has learned only less data. Okay. And then good balance. If you see the good balance curve, the data is like this and the point and the machine learning curve is also on the proper points, or it is going through all the points. Okay. Now we have seen these terms. I'm not explaining them. Training set, test set, training set, validation set, test set. Okay. Now to start with, the first is hold out method, or this is the basic approach. Okay. This method simply divides the entire dataset into two buckets. That is, here we can see one is training dataset, another is testing dataset. Depending on the use case, the data might be 70-30, 60-40, 70-25, what is written here. But mostly, basically, we'll take 70-30. Basically, we use that normally, but it depends. 80-20 also it can be, 50-50 also it can be in some data sets, or in when you're training sometimes. Okay. The catch is because this split is happening randomly, you can't be sure which data ends up in which bucket. This causes the accuracy to fluctuate every time the split changes, leading to high variable test error rates. Additionally, using only a fraction of your data to train can introduce high bias. That means whatever important data can be in the test and we are not putting in the train. So what will happen when you are training with this data set, but when you are using them to test, you will not getting proper output because the data also that we needed to train the model, it's left out in the test. It's not given into the train data set. Okay. So next is cross validation or k-fold cross validation. So cross validation solves the instability of the holdout method. Instead of one random split, the training data is split repeatedly and multiple models are trained to get much more stable and thorough evolution. So how does it works? The data is, if you see here, the data is partitioned into k equal, so you have k like 1 2 3 4 5. So if you see cv, that means k is equal to 5. Okay. So it is partitioned into or equal size, or we also call as folds. So see 1 2 3 4 5 folds. Okay. So the data is partitioned into equal folds. The models on 4 folds is evaluated on the one remaining test fold. Okay. So one of them will be test fold and is evaluated on the one remaining test fold. This repeats 5 times so that every fold acts as the test set exactly once. So if you see here, 5 split, the first time one is taken as a test, this one as a test, 3 4 then 5, and remaining one is used to train the data set. So what happens by doing so is every single example is in the training set exactly once, making highly efficient or effective use of the data. Furthermore, as the number of folds increase, the variance also decreases. But there is also another drawback to this, or there is a drawback to this, that is it increases computational cost because you have to train model multiple times, or you are training multiple models. So split 1, split 2, these are all different models, right? So you're training the model 5 times, so that is computational heavy because we have to train each model, so that takes computation, right? So next, if you see here, we have seen a benefit of cross validation. Each example the model needs as data more effective 5 cross in each iteration, use 4/5 of the data to fit the model. Number of k increases, the variance also decreases. The main advantage of cross validation is increased computational cost. I have said that the biggest disadvantage. Okay, and also it's not considered suitable for imbalanced data set. So next we have stratified k-fold cross validation. So how does it work? K-fold splits data uniformly, which is dangerous if you have imbalanced data. For example, if the data is 90% dog and 10% cats, for example, two categories are there. One is 90% dog, and remaining 10% is cat. So it will not work properly. So for that we have stratified k-fold cross validation. Okay. So what happens here is, how does it work? Standard k-fold split data uniformly, which is dangerous if you have imbalanced data. So stratified k-fold, what it does is, it uses stratified sampling to ensure the proportions between classes in each fold perfectly match the entire data set. For example, if you see this is an imbalanced data set, see number of female is here, number of male is more, right? But what it does, it balance. So imbalance distribute in each fold. In each fold the proportion will be same. Okay, here we are not seeing the proportion, okay, in cross validation. But in stratified cross validation, what you're doing is, you are, because the number of female and number of male, see number of female is less whereas number of male is more, so this has to be maintained in all the folds, so one fold, two folds. So that is what the difference here. So it is maintaining that. Then we have leave out cross validation. So how it works, instead of dividing data into larger subsets, a single observation is chosen as the test data and everything else is used to train the model. So what is the benefit? The benefit is it provides unbiased estimates. The drawback it has extremely high variance and computational massive, because the model must run n times to test every single observation. So what is there? Instead of dividing the data into subsets, we select each single observation as test data and everything as label. So if you have 1 2 3, we will take one as test, and all the other things are will take as for training. But what is the issue? We have n number of it, may like if we have 1,000, so it has to be trained for 1,000 times, and that is very high computational it will take. So that is like wastage of computation. So that is the biggest disadvantage. Okay, the next you have shuffle split cross validation, also known as Monte Carlo cross validation. So what is shuffle fit? Instead of fixed folds, this method randomly shuffles the dataset and splits into training and testing states based on specified proportion, repeating the process n times. So it will shuffle and it will do number of given splits that we have given, like in k fold. But here we are also shuffling so that every split will be different. So unlike k fold, some data samples might never be selected for testing or training across all the iterations, because we are we are shuffling. So one shuffle, it can be like one guy is not never coming in one, like for testing. So that is one drawback. Okay, in shuffle split cross validation. The next we have time series cross validation. So in time series cross validation, you cannot randomly shuffle time series data. So this is for time series where time is related. So see, training set and also time is given. So in this, you cannot randomly shuffle time series data. Instead, data is split chronologically, also known as forward chaining or rolling cross validation. You start with a small subset of historical data to predict later points. Those newly predicted samples are then included in the next training dataset to forecast even further into the future. So what means is, here we have seen, like it's called forward chaining. So it's small subset of dataset we're trying to predict and checking the accuracy of the later part. For example, if this point we are trying to check, okay, this point is coming like this, so on and so forth. Okay, so that is what we are checking, and we are checking if the accuracy is good or not. This is only for time series. So time series is different from other, because here time is also related. Okay, the next, bootstrap. What is bootstrap? This method uses sampling with replacement. When drawing a sample from data set of size n, the probability that a data point is not selected is 1 minus 1 by n. Over a full bootstrap sample, roughly 63.2% of the data is drawn at least once for training and leaving out 36.8. So if you see here, the meta score 0.632 because after drawing sample n times, roughly 63.2 data is drawn at once and 36.8 data is never drawn. Okay, these untouched out of bag samples are then used. So this test is used for evaluation. So only 63 is drawn at least once, another 36.8. So this is good for untouched data. Okay, for seeing like how accurate is your model. Then finally hyperparameters. Okay, so what is hyperparameters or what is hyperparameter tuning? We'll learn that. So hyperparameters are variables that the user specifically uses usually while building the machine learning model. The majority of the machine learning models contains hyperparameter that can be adjusted to how the model learns. We have so many: max depth in random forest, k in knn, we know that, right? Kernel in SVM, like kernel we have linear, non-linear, k number of k, then max depth in random forest. So our what is our goal is to find the best parameters to get the perfect prediction result from our model. Okay, one is hyperparameter tuning. Hyperparameters determine the behavior and performance of machine learning model. These parameters are not learned during training but are instead set prior to the training. So the process of finding optimal values for this hyperparameter is known as hyperparameter optimization. The grid search algorithm would train a model using every combination of these values and evaluate the performance of each model. Okay. The randomized search algorithm will sample values for each parameter from its corresponding distribution and train a model using the sample values. So we are trying to find out which are the best parameters. So not training the model, we are trying to find during with each iteration which is the best parameter to get the best output. We are seeing different things. Okay. So parameter sorry, parameter tuning during cross validation. While the method of splitting the data into training validation test is quite sensitive to how exactly the data is split, for better estimation, the generalization performance, instead of using split, we can use cross validation. We have learned cross to evaluate performance of each parameter combination. So using cross validation and we are changing the hyper parameter tuning. So every iteration, for example, we'll see here we have example for SBM. Once we'll try with linear kernel, once we try it non-linear, we will find out which is the best accuracy. We'll use what we learned, this cross validation, right? We'll use cross validation to evaluate the performance of each parameter combination, right? So we are doing to do that. Then we have something called as grid search. Grid search uses a different combination of all the specified hyperparameters and their values and calculates the performance for each combination using the cross validation method and select the best value for the hyperparameters. This makes processing time consuming and expensive based on the number of hyperparameters involved. Here C gamma kernels are some of the hyperparameters of an SVM model. We know that C gamma kernel. Then how do you pick the best value for C? The best value is dependent on the data used to train the model. Okay, so we will find the base value dependent on the data used to train the model. So this is important. The sample grid search, we can see like different score. We are finding the scores for different time. One is for gamma, one is for C. We are doing different searches. So we'll use different combination to calculate the values and using cross validation method. Then we have hyperparameter tuning. We'll see. Mm. Then finally we have randomized search. The last in randomized search, instead of trying everything, randomized search in samples a fixed number of combinations randomly from specified distribution. So what is there, like if you try to find all the combinations, for example 0 to 1000, we have to try for 1000 times, right? Instead of that, what is randomized, we will give, for example, you try 50 times, or yes, we give 50 times. So instead of trying all the 1000, it will randomly pick one, like 50 values, for example 365, 385, 280, like that, 50 times, and it will try to get the values, and which is the best it will pick out. So here what we are saving time, but there is one catch here. The catch is it does not explore all the entire search page. So major benefit can be, we can reduce, for example, the base parameter is hidden somewhere and we leave out that parameter. So what will happen, will not get the best accuracy and other things. So that is what is keeping out. So it's like if you want faster results, we can use this, but it will not give the best results. Okay, so that is the difference between what you have